Okay, it's 10 o'clock. This underwater shock course or underwater explosion course for 6 weeks, as you are learning, I try to cover a pretty good amount of the knowledge. So, but please review what we provided as a lecture note, and this lecture note Higyu really helped me to bound this. This is a result of what I lectured before, but of course a lot more could coming in, but this is pretty fundamental things. So you can have something on hand, then you can read. All my lectures are in this lecture note, so I think this will help. Then you don't have to, we don't have to send you the email with a lecture note attached in there. So you can just bring it or just open it and learn, okay? Okay, so now we have to solve a wave equation. So which is what this equation is. This is a one-dimensional wave equation, and general wave equation, I don't suspect you saw the wave equation, right? Yes or no? This is a general wave equations here. In undergraduate physics course, I think it's mandatory to take the physics course in undergraduate curriculum. Sungtae, yes or no? Yes, right? So you, any wave propagation, in OSC we have a course regarding the wave propagation, as I recall. Maybe some of you may take that course. Anybody? Professor 최우영 교수님 or 조연우 professor, have you taken the wave, mechanics of wave? No? Have you seen this wave equation before? Oh, you forgot to say something, yes or no? 주일이 wave equation 언제 take 한 적 없어? solve 한 적? 정호? It doesn't matter whether it's 5 years ago, 10 years ago. Once it stick here, of course it's not going to stay here a long time, because you have to bring another type of the knowledge, then of course slowly it goes away. But when you are exposed again, so it's coming back very fast. So learning never disappears. So anyway, in conjunction with underwater shock, we are using the underwater acoustic approximation to do all the computations and all that. So we are again in the position to solve the wave equation. This is what the wave equation is. Wave equation, wave really means wave can propagate not only in the water, but it will propagate in the air. It will propagate any material, any solid, liquid, or the vapor or steam. The wave will propagate. If there is no air, for example, no medium, then of course, if it's a vacuum, then wave doesn't propagate. It's not compressible. It has to be compressible media to propagate the wave, right? So here right now we are in the position to solve the wave equation. P is here our interest is of course a shock. So you can say shock wave pressure, or you can say acoustic wave pressure, depend on your interest. Then C naught, you know, in this case, propagation occurs in the water. So C naught is, of course, acoustic speed in the water. And naught implies, treat that as a constant for underwater explosion problem, okay? So first, we're going to deal with the plane wave. And second, we're going to deal with the spherical wave. So plane wave, I said here, is a one-dimensional wave. It propagates in, here I said X direction, but you could set up as a Y direction or Z direction. So here, just to pick out the X, saying the one-dimensional wave is called a plane wave. It's a plane wave moving in X direction. Then this Laplacian of P is expressed as this. Then for plane wave, second term and third terms are equal to 0 because it propagates only in X direction. Then you can simplify this 3D wave equation into the 1D equation. So now we are in the position to solve this equation. Second order, the partial differential equation. And this type of the equation, you know you have done that before. I think Woo-Young Choi, Professor Woo-Young Choi is teaching this quarter some numerical computational approach. I think you might solve this problem there already. Very popular, but a very popular set of equation to solve, but here has a goal in it. It's not just solving, no fun. If you just walk without the direction, no fun, right? With the direction, it makes sense. Here, our interest is really shock wave motion, shock wave propagation. That's what we are working on it. So here is x-directional motion, and the well-known D'Alembert solution, we just pronounce in Korea as a D'Alembert, but D'Alembert is all same. General solution. What does it mean this is a general solution? General solution means this is a f and g is arbitrary function, okay? If you replace p with this, then equation satisfies by itself. Okay, both right and left hand side identical if you put this in. So this is a well-known, the general solution called D'Alembert solution. I think years back he first posed this solution set. And the f function is, I called here, the forward traveling wave, forward. So wave has, let's say, x-directional wave. That's F, okay? If it hit the wall, then reflected back, that's called the backward. I call the backward traveling wave. So for the one-dimensional wave, plane wave has a forward traveling wave and a backward traveling wave. So that's what the reality is. Then after that, it's all bouncing back each other. So that's what this expression, general solution expression, implies here. And the C naught is, as you see in 2.2, square root of the dp over d rho. Usually standard the environment or condition is 20 degrees C in seawater, and usual value, the basic value for C naught is about 5,000 feet per second. We can convert into the metric, which is about 1,500 meter per second. I said about 100 times already, right? Yeah. Yes. But this is it. Then you can, this is a time domain function, t minus x distance you travel divided by C naught, then that's a time function. So you can work in the time function. But I gave some thought, how can I show to the students more explicit sense? Distance, you can see it. Time flies away. Of course you can see it. You can just work on the time domain. I look at down here in the distance domain, x, okay, how I can explain a little bit easier way. I don't know whether it's easier way, but it's, so what I did was, okay, I'm going to pre-multiply C naught here, then C naught drops off. I can set up the general solution like this. Question is this really general solution? Then to verify, what do I have to do? What do I have to do? All I can do is, if I plug this P into here and here, if equation doesn't satisfy, then does not satisfy, then that's not the general solution. So if you plug this into here, you satisfy that one-dimensional wave equation. So I can claim that's okay, that's also general solutions. Then I can say, all right, in this situation, if I draw the x and p at t is equal to 0, at t is equal to 0, then I just draw the f functions and g functions right here. T is 0 minus x plus x. Then the function should be something like this, whatever the wave form in the position. Then I can say, how about just to flip these two terms? If x was here, t, c naught was here, I flip this. Is it okay or not? Then if you plug into the 1D wave equation, it satisfies. Okay, this is another good general solution. Then I say, how about just explaining the wave motion using the distance concept? So let's say at t is equal to, considering first the f function for the traveling wave, okay, first, let's say at time t is equal to 0, is position gonna be, you can draw the reference position, it's right here. Then I can say, okay, at time t is equal to t naught, then it traveled the distance x, then it traveled forward, the position was here, it moved down to here. At t naught time, the distance it traveled was from here to here, So c naught times t naught it's just to try to explain a little bit better, but some of you may, I can work on the time domain. Go ahead, you work on the time domain, okay? So then I can say c naught times t naught, this is the distance it traveled during the t naught time. Then to get it back to original position, you have to subtract the c naught t naught from x. Okay, then you can say, this is a forward traveling wave. I don't know whether, it makes more sense or not. It's explanatory position, the situation. And for backward traveling wave, that means the wave is moving in the backward, the minus x direction. So initial, original reference position to the final position at x. To get it back from the t naught position back to t is equal to 0, you have to add the c naught, t naught to x. That's what the backward traveling wave, okay? So then a general solution contains both a forward and backward traveling wave. Okay, so with that, with that general solution set, so now we're going to specialize. We are going to specialize the wave traveling in the forward direction. Explosion occurs, okay? And the incident shock wave is always, let's say, propagating in the radial direction if it's a spherical charge. Okay, that's fine if it's a huge nuclear charge, and at the time of explosion, of course, it will propagate in any direction. I'm going to say one radial direction is x. As it really travels farther and farther, then it becomes the one-dimensional wave because curvature becomes infinity. It's a flat, okay? So this is a one-directional wave called the forward traveling wave. So I'm going to say, okay, I'm going to consider the f is equal, p is equal to just a function of f, okay? It's just moving, propagating x direction. It's understandable. Our idea is to get the solution of one-dimensional wave equation. So that's the direction we are pursuing. And have you seen this before? Hyunchul, have you seen this? Hongshik, you may not seen this before. May or may not. May not. Because you were sick. Next week is not going to be excuse. So if you review, this is called what equation? 성태. Momentum equation. Within the momentum equation, there is a partial derivative. Second term drops off because which is a scalar product of the v and the gradient v, which is getting smaller and smaller. You can neglect that term. So this becomes that equation set, easy to handle, partial rather than partial means is one parameter dependency. So then it's easy to get the solution from the partial rather than total derivative. Total is a function of t and x, y, z. It's all in the book in section 2.3, okay? You can look at over the weekend. Well, you know. So del V, what's the V here? Jongho, what's the V here? Velocity vector, right? Which is ui plus vj plus wk. ijk, unit vector in x, y, z direction, minus 1 over rho naught gradient p, okay? Spatial operator. So this is called the reduced momentum equation. Remember? Yes. Where? Page 2.3-1 in the lower part. So now this is the equation. This is a general solution. So what we did was replace P expression as F into right here. Okay. If you do that, F, then this is equation. I replace P into the F. Then there is a F prime. Okay. This is a prime derivative. So to avoid any confusion, I rewrite over here. Del F parenthesis whole function over del X is equal to del F over del parenthesis. Differentiate with respect to whole thing, whole parenthesis, okay? Is easy to understand. Then del parenthesis over del X. This parenthesis is right here. T minus X minus C naught. Okay? So you have to differentiate partially with respect to X. X is right here. It's doable. If you do that, what do you have? If you differentiate this function with respect to X, then it's a minus 1 over C naught, right? Say yes. Yes. So this, if you do that, is minus 1 over C naught. This portion I called F prime. Don't confuse it. This is F prime, and this equation set comes like this. Okay? So if you do the differentiation, the partial with respect to X for P, then it's going to be the minus 1 over C naught. So 1 over C naught here, minus minus becomes positive, rho naught C naught, then F prime. This is F prime, as is. It's very good because what I'm going to use later is integrate to get expression for the P and U. That's what I want. So when you integrate, I can integrate the with respect to the parenthesis, which is very nice, can be done very nicely. I can explain better than this because I go through this at least 100 times in the past, delivering lectures and all over the place here. So here, this is, put the mark here is F prime. So now, integrate this equation with respect to time t. So if you integrate, you can move this guy to here, then integrate. So if you do that from time t naught and t naught and t, T naught is initial time. Initial time. Okay? You can say in reality, initial time means if you consider the detonation time as T is equal to 0, I can say fine, you can do that. But our interest is what happened when the initial shock wave hit the target, then propagate, giving the damage to the target. That's our interest, right? So you can set the time that the shock wave arrived at target as T is equal to 0. You can do that, of course. It's just shifting. In this case, it's as a general, just using this equation and take integration from T naught to T. This is F prime. Okay? Then if you integrate some students wants to see derivation I show in the next page. If you do that, you will have a beautiful, the shock equation. Very important equation. I said about 10 times maybe. U minus U naught is equal to the 1 over rho naught C naught P minus P naught. Okay? Very important equation. How can I physically tie with this equation? Like this. This is a 1D wave, right? One-dimensional wave, plane wave. This is a wave propagate to a positive x direction. Then behind this incident shock wave, you have a pressure P and the fluid particle velocity U naught. You can say this area is fluid, and fluid is collection of the fluid particle. Then it's all over the place. Okay, it's all same U behind this incident shock wave is U. In front, okay, in front, of course, is a fluid, right? So I'm going to call that initial state for the velocity, fluid particle velocity is U naught and the pressure P naught. Until shock wave comes, everybody feels, oh, fine, it's not going to come. That's what happened to tsunami. In Fukushima, everybody feels it's not coming. It will never happen because in Fukushima, in the past, it never happened there. Before some other place it happened. It's not coming. Then everything is all calm. So nothing happens. It's a breeze. It's so good. It's good. Then bang onto it. That's what the explosion is. That's what the gas explosion is. That's what the fire is. It's all same which happened in the disastrous situation. It does not give you warning. So it's called in industry accidental situation. Accidental situation. What happened? Okay? So this is what happens. So consider this is the shock wave propagating x-directional for plane wave before usually U naught is equal to 0. Then you could say, well, when I see Yeonpyeongdo accident, there was heavy tidal current, and the fluid has a wave, then it has some flow speed there. Regardless, for underwater shock situation, you can assume with with a good sense, I can say, you can set U naught is equal to 0. It's not the accidental situation in the regular flow. I have a current moving, with a certain fluid particle velocity, then bang onto it. You can comfortably assume U naught is equal to 0. And P naught, you can set equal to 0, depend on the depth of the water. For the depth, if it's going down to deeper, then the pressure is not equal to 0. It can be a 2 bar, 1 bar, 3 bars, whatsoever. Okay? So then you can deal like this, saying, okay, I'm going to set this P naught equal to 0. My interest is really what the dynamic pressure carrying by the shock wave. In other words, I'm going to set the P minus P naught as a dynamic pressure, or people call the gauge pressure, what the gauge register. So what you usually do is before you conduct the testing, you put the pressure gauge in the water to the certain depth you want to test, then go down to 10 meter, then it registers 10 bar, then in the instrument you reset to 0. Then after that, whatever it registers in the gauge is going to be the dynamic pressure due to the explosion. That's what you usually do, okay? So this is a this is really tie with this equation, explaining the physics well, okay? Rho C in the water. Rho C is called the characteristic impedance. Impedance characterize the media. For the fluid, for the water, the value, standard value is like a 5 pound/second per inch cube. Okay, if you just calculate the units of this, it comes out like that: 5 pound/second per inch cube. Okay, it's called the characteristic impedance, or simply you can call as impedance. Okay. Then when U naught is equal to 0 and P naught is equal to 0, then you have this equation set. So P minus P naught, delete the static component of the pressure, remaining part is a dynamic pressure. So you can say P minus P naught is simply P. If you set the P naught is equal to 0, then you see the really nice equation set. P is equal to rho Cu. I talk on Monday morning about that. P is equal to rho Cu. In the final exam, if I give this as, if I ask you write the PV, PU relations, if you can write it down, this equation, zap, just your paper is 0. Because this is so basic, so important. You can afford to lose from your mind. Shock pressure is equal to impedance, rho C times U. U is a fluid particle velocity behind the shock wave. Okay? That much important. No, you don't have to memorize the things. So over here, the deriving this, solving this equations is shown down here. I want you to surely sit down in your the working space and go through this. Some students once I go through this, wrote this, and I included in there, in your notes. It's there. Yeah. Now the spherical wave. So we did for a plane wave, a spherical wave, and plane wave. What's the difference? What's the basic difference between the plane wave and the spherical wave? Hmm? Yeah, yeah, that's what we talk. And plane wave is one-dimensional wave, so wave pressure is constant. It's keep moving. Doesn't, it's infinite plane. But for the spherical wave, as the wave propagates, surface area is expanding. Energy inside the sphere is constant, but as it propagates, what happens? Then area is getting larger, right? Then the pressure per unit area should be getting lower, right? Because the area is getting larger. So that's what the spherical, the wave, nature of the spherical wave. So I can say for spherical wave, the V is equal to UR times R hat. R hat is unit vector in the direction of, in the radial direction, like I hat, J hat, K hat. Okay, it's a unit vector in the radial direction. Because V is a vector, so radial velocity, then I can express UR. UR is the velocity. The velocity, fluid velocity in the radial direction. That's a scalar quantity, of course. R hat is a unit vector pointing in the radial direction. So spherical wave is concerned for looking at the pressure propagation. That's really point symmetric. In the spherical coordinate, it is a function of R, but not the function of the theta or psi, as you will see here. Because it's all point is the same in the spherical surface here. Radial pressure P is a function of R only, because in the spherical surface, any point you pick up, the pressure is the same. Point symmetry, I call. Okay? Make sense? Yes. Then we have to bring back the reduced momentum equation. So this is the same reduced momentum equation. Del U R over del T is minus 1 over rho naught del P over del R. Rather than X, I use the R. Okay? This is the radial direction R. Radial is R. Makes sense? Equation 2.3-1. If you look at page 2.3-1, it's there. In the second page, you have this. This is the second 2.3-2 page. And V is UR, R hat. Then you differentiate with respect to the time t. Once again, you have the last equation set. You have the last equation set is here, down here, no problem to differentiate once more. Then from here, this is a scalar dot of gradient operator dot r hat. This is a scalar. R hat, this is a unit vector in radial direction. From here to here, it's so fun to derive that expression. I feel it's so fun, and try it. You don't have to submit. If you really dare to see the solution, Higyu has all the solutions, but you should be able to derive yourself. One good point is R hat. You need to find the expression like gradient, okay, in a spherical coordinate. You can have a Laplacian expression. You can have there always, but find in internet or any textbook like a vector analysis. You should able to. You don't have to derive all that. It's coming as pretty well-known expression. So find the expression for. God bless you. Get the expression for the gradient in a spherical coordinate, then you can apply the scalar product, then you got that. You follow me? So get that. If I say get that, please do. Who knows? It's not a threat. But I may put this in the one small item in the final. I'm going to give you the final on the week of 17 December. You notice that the email from the school about the final exam supposed to start 14 rather than 17. I think it's because of the vote, right? Presidential voting. I don't know why they do that, but that's what they announce it. So we're gonna do, I'm thinking 2-hour exam only for shock part. The other part you submit it for fire and gas explosion, you are writing, get ready at the end of the month, this month to submit. So 17, 10 o'clock? 10 o'clock to 12? Or 9 you have another class, maybe exam, right? So 10 to 12, we're gonna have some exam time. I didn't give you much homework, but you will get a few homework before the 14th of December. So do this, I said homework. In the past, all the students did it. I said you don't have to submit this particular homework, but please do. So then you get that. Then now bring back, we are doing the spherical wave, now bring back, what do you call this? Wave equation. This is nothing but the wave equation. Del square P, Laplacian expression, is readily available anywhere. And this is a spherical coordinate that I'm using here is r theta psi. Theta is here and psi is here. Some book shows theta and psi flip. So you have to be careful. Not always the same. So theta is measured from the vertical axis. Psi is from xi. Theta r. And so if you expand the Laplacian operator, it comes out like this. It's a 4 term, 1, 2, 3, 4. Except the first 2 term, third term and the fourth term is really del partial derivative is concerned is with respect to theta and the psi. But this is, we are working on the point symmetric point. And really pressure, velocity is independent of theta angle or psi angle. Anything derivative with respect to theta or psi, you can zap. You can delete that. So I can say third and fourth terms you can delete. Only keep first 2 terms, which is a function of r. Okay? Clear. First and second term, you can combine them together and re-express as this. In the parentheses, you have R and P. Okay? Or you can reduce down into that forms here. Okay? This is a basic, this equation bring back to the left-hand side of the wave equation. So you can plug in identical to this. Nothing is. Then I can claim that R is a spatial coordinate and independent variable of time. Then I can R put in associate with P. Then left side RP here, right hand side is RP there. That the resultant equation is like this. If you look at, replace RP as P1, it's like, this is identical to this. By looking at this, if I just change this form as replace 1, what this equation look like? This equation is same as the plane wave equations. I just did replace P1 by P, okay? Then identical to plane wave equation. So plane wave equation, we know the solution already. So because we solve the plane wave equation, so over here P1 happened to be RP, that's a P1. First, for the plane wave equation, first term was forward traveling, backward traveling. But in this case, I put P1 to RP. Now this is a propagation of wave is concerned in the radial directions. So now I put it back P1 to RP. So now R, I'm going to move to here. So this is propagation is in the radial direction. So first term would be outward traveling wave. Outward means still in the radial direction. Then you have a mirror surface in the spherical shell, let's say. It's nothing but ball, okay? Then as this is a source at the center, as a source hit the end of the mirror, it will reflect back to where? In the same center, same spot, right? So that's a backward traveling wave. That's in spherical shell is inward traveling wave. First one goes outward traveling wave. Reflection wave is an inward traveling wave. Special case, isn't it? It's like a ball, right? And you paint the mirror surface right inside. When explosion occurs at the center, bang, goes to the middle point, then coming back to the same point, right? That's what the case is. Outward traveling wave, this is an inward traveling wave. So now considering like forward traveling wave, I'm going to pick out the first term, not the reflection part first, which is another name is incident shock wave, right? So that's what this outgoing the wave. This is same 2.3-1. Then plug back in P for the 1 over R multiplied by function P, right? Yes. Then you plug in, then you differentiate first by R, second by function F. Then you have two terms. This is first, and this is second term. That I want you to do actual calculation. Over here, this is F prime. Okay, F prime. So F prime is this, as we discussed before. Then you integrate, right? First differentiate, integrate. So as you integrate, it comes from time t naught to time t, first term and second term. Okay, then what you do is just to change this term for this term as a second. As you look at carefully, 1 over R times F function, this one, and this is at time t naught, this is time t, which happen to be P at time t. Second term is P at time t naught. If you look at this equation without the second term, which is identical to the plane wave solution, no difference. But this portion, so-called after-flow term, or sometimes it's called the surge term, S-U-R-G-E, surge term, which is a function of R here. If R is getting larger, it converges to what wave? Plane wave, right? If R is large, long, then what happened? This term is equal to, approaching to 0, 1 over R. So naturally, when the spherical wave is way farther out, then it converges, spherical wave, it converges to the plane wave. Curvature effect is none. But after flow term, as you look at here, this is the history of shock pressure. A term happened to be there. So sometimes when you deal with the underwater explosion problem, this term could go 10%, higher than 10% of the total. But as it moving way farther out, then eventually this term disappears. Okay, I think I'll stop right here, and we'll move on. Any question? Explain, clear? Say yes, it's clear. If it's not clear, problem clear? Abdullah, should be clear. Yeah. Okay, I'll see you Friday morning.